Welcome everyone to this week's Zoom for Thought talk, during which Nicholas Seeger will tell us about a quasi-pseudo-semi-kinda combinatorial-ish topic. Take it away, Nick.
Thank you, Vaki, and good afternoon to all of you guys. So, as Vaki was sort of mentioning, I will be talking today about pseudo-quasi-random Boolean functions. And hopefully by the end of the talk, you'll see the reason why I am putting so many weasel words on the front here. So roughly my outline, we'll be going over a bit of a motivation for the whole area, then we'll get into something called theories of quasi-randomness. Then I'll introduce the topic that I am really focusing on in this talk, which is Boolean functions. We have the Quasirandomness theorem for them, and then we'll talk about how everything kind of explodes and things start going wrong very drastically, and that is where we will start to see some of the extremely non-combinatorial parts of this talk come out. So, without further ado, let me start off with a fairly simple problem. I roll a 6-sided die 120 times in a row. I'm going to get the following sequence of values: 21s, 22s, 23s, 24s, 25s, and 26s. Okay. Now I'm going to tell you that this is a fair die and I made 120 independent rolls each time. How many of you believe me on this? I'm seeing some pretty clear no's, and you shouldn't believe me on this. This is an utterly absurd claim. But of course, I mean, if I do roll a fair die 120 times independently, this is a possible outcome, though. At the same time, this outcome, there's something about it that seems fishy if I'm claiming that this is entirely random. It has a lot of structure to it. It has a lot of patterns in it. And basically the question that I'm building up to is, let's say I give you some sequence of these 120 dice rolls, and I want to quantify the notion of how random is this sequence. So I give you some combinatorial object, typically, and I want to run a battery of tests on this object that certify with some parameter whether the object looks like a random object or if it looks like a determinist. So rather than being abstract, let me give you a few more examples. So roughly the way this is going to work is we're going to come up with some test. We'll compute it in expectation on a genuinely random instance. And then we'll essentially say that our object passes the test if the value that pops out of the test is close to the random value, and it fails the test otherwise. So my first test, keeping in mind the same sequence that I mentioned at the beginning, is what's the average value of the sequence when we compare it to a random sequence? Well, in expectation, a random sequence would have value 3.5, and well, this one does too. So this is probably not a very good test for us to consider. But the idea of averaging does have some merit to it, because I'm going to do something a little bit different. Now I'm going to, instead of looking over all 120 elements of my sequence, I'm going to look at subsequences of length 10. And I'm not going to look at just one of them. I'm going to look at all of them. And essentially what I'll be computing is the maximum over all starting locations of the average of the next 10 elements compared to what it would be in expectation, which is 3.5. So basically it's the same idea as what we were doing when we were taking the average. It's just now we're sort of zooming in and we're looking everywhere at once. And here, the maximum difference of a subsequence of length 10 is going to be 2.5 away from what it would be in a random sequence. And this is pretty dang far. This gives us one sense in which our sequence is not random. And I'll actually ask another question. Here's another test that I'll give you, which is, how many times does a particular subsequence of two numbers, specifically the subsequence 2, 1, how many times does this appear? Well, it doesn't. We had 1s followed by 2s, 3s, 4s, and 5s. So we never have a decrease. But if my sequence were actually random, in expectation, I should have about 3.3 of these, with some small variance. And if I were to make more and more dice rolls, this number would become more and more as things go. And so the basic idea of what we're going to be doing here is we will have a bunch of these tests. And we're going to formalize this into something called a theory of quasi-randomness. And this is my first weasel word for it. What it's going to do, and the really, really key idea about quasi-randomness is I'm going to have a gigantic list of different tests. On the previous slide, I had 3 of them. One of those we can ignore, the test of just the average of the whole sequence. But I have 2 others, averages over subsequence of length 10 and counts of fixed subsequences. And the whole idea of the theory of quasi-randomness is that I can get a bunch of these different tests and prove that if my sequence passes one test, it passes all of them at once, up to some small losses in parameters. In a sense, we're saying that there is a notion of randomness that can be expressed in 5 or 6 different ways all at the same time. And all of these ways are equivalent to each other. And to basically the easiest way to see what this looks like is to talk about the prototypical example for a theory of quasi-randomness. The Chung-Graham-Wilson theorem was published in 1989. So here's our setup. I have a sequence of graphs on n vertices with n squared over 4 edges. Think of n as going to infinity. The following tests essentially are going to be equivalent to each other up to little o1 terms. My first test is that every labeled graph on k vertices, and k is arbitrary here, which makes sense since n is going to infinity, will appear as a subgraph of my graph G, approximately 1 plus minus little o1, n to the k divided by 2 to the k choose 2 times. Don't worry too much about the specific formula here. The key point that I want you to get out of this statement is that's about as many times as it would appear in Gn 1/2, the graph model where I pick every edge independently with probability 1/2. So this is my first test. My second test is much, much simpler. I'm going to pick a 4 cycle, a graph on 4 vertices and a little box, and it's going to have to appear as an induced subgraph about the same number of times as it would in Gn 1/2. So this is my second test. My third, take the adjacency matrix of my graph. So the matrix formed where the vertices index both the columns and the rows, and the entry of the matrix is 0 if there is an edge between the 2 vertices, and 0 if there's no edge, 1 if there is an edge between 2 vertices. Take this matrix, compute its largest eigenvalue. This should be theta of n, should grow with the size of the matrix. The second largest eigenvalue should shrink relative to the biggest guy. Those of you who are familiar with the terminology, this is another way of stating that this graph has to be a spectral expander in order for this condition to apply. And finally, my fourth condition is going to be that if I pick any 2 subsets of my graph, S and T, and I count the number of edges going between them, it's about the same thing as it would be in a random graph. So each of these is 4 very different looking tests. One of them is, the first test is practically impossible because you'd have to check literally all finite fixed graphs. The second test, not too bad. I can just count over all quadruples of vertices. The third test is even easier. I just have to compute 2 eigenvalues. The fourth test, while not impossible, is annoying to compute. And the claim of this theorem is that if I want to pass any of these tests, I just have to pass 1. All of these tests are capturing, in some sense, the same notion of randomness. And this is really the key idea behind quasi-randomness, that there's this equivalence theorem proving here's all these different ways you can characterize randomness for a particular object. So before I proceed any further, are there any questions on what's going on in the theorem or what I've been explaining so far? Okay. So the Chung-Graham-Wilson theorem, it really did start the theory of quasi-randomness when it first came out. And there's been a lot of work done ever since. In particular, you can do quasi-randomness theorems for other kinds of objects. For instance, subsets of Z mod n, permutations. And then we get to the tricky one. This one took about 15 years to fully figure out, but there is a quasi-randomness theorem for hypergraphs. There's also some for bipartite graphs, Cayley graphs. As you can tell, this is very popular in graph. But there's other guises, if you will, or other names that this sort of theorem gets attached to. If you've learned any results about equidistribution in analytic number theory, it is another way of stating a quasi-randomness theorem for the digit sequence of a number. Basically making claims about how often does each digit in a particular base appear in a decimal expansion, certain statements about exponential sums, etc. Probably the closest related subject that is essentially quasi-randomness is the other weasel word for my talk, which is a structure versus a pseudo-randomness proof, often from additive combinatorics or theoretical computer science. These theorems we're going to be hearing a little bit more later on. Another classic example is property testing in complexity theory, which basically asks, give me some object. How do I test if it satisfies some sort of randomness condition? Quasi-randomness theorems are lurking in the background. And last but not least, something of a duh example, cryptography at the end of the day is centered around the idea of here is a deterministic object that we cannot distinguish from random noise. Roughly speaking, something for which a quasi-randomness theorem applies. So you may have seen some of these same topics, albeit under different names. And there's kind of a template to all of these theorems. For those of you who are a little bit more minded towards category theory, my suspicion there might actually be a way to truly generalize all of these theorems into some deeper categorical theorem, because many of them end up looking quite the same. In particular, there's a few tests that no matter what combinatorial object we seem to be looking at, it almost always has a few tests that look like this. First one is going to be a count of some small sub-object. In our case, in the Chung-Graham-Wilson theorem, that was counting the number of subgraphs of fixed size. The next test is a count of, quote, structured small sub-objects. Here, this was counting 4 cycles, i.e. we have a particular sub-object or small collection of them that is somehow controlling all of these things behind the scenes. The third test is some sort of eigenvalue or Fourier coefficient-based test. And here, that happened to be talking about the 2 eigenvalues of the adjacency matrix. And finally, there's going to be sort of a dual condition to the first one. In the first one, we counted small sub-objects. In the final test, we'd take an average over large sub-objects. And more often than not, the sub-object is the same in both cases, or very closely related. Here, in this case, it was the number of edges between 2 large subsets. So today, what I'll be talking about is a quasi-randomness theorem for a different combinatorial object than what I've been talking about so far, which is Boolean functions. And again, this would be a good time if you have any questions about what I've been talking about now to ask for clarification. So are there any questions at the moment?
Yeah, is there a particular reason we're using? Oh, yeah, JD, go ahead. Go. Or I'll start. Is there a particular reason we're using 4 cycles? Like we're counting the number of 4 cycles as opposed to counting the number of 3 cycles or 5 cycles? Like what's the significance there? Or is it just an arbitrary choice?
It is not an arbitrary choice. If I counted 3 cycles, this theorem is not true. If I count 5 cycles, this theorem is kind of sort of true, but not very. Basically, like it really should be 4 cycles. And course. The reason for that, the count of 4 cycles is the first cycle count that is not completely controlled by the spectrum of the adjacency matrix. If I tell you the spectrum ahead of time, if I know some basic facts about the spectrum, I already know exactly what the count of triangles in my graph will be. This is something that you can fairly easily compute. Once you get to C4, you need some additional information. And that's actually why it's the first cycle length that genuinely gives you some control over properties of the graph. Very good question. Okay. Are there any other questions? Yeah.
Yeah, so my question was, you were saying you thought maybe there's some sort of deeper generalization of this. Do you think people have tried this before, or is this just speculation?
This is entirely speculation. I have not seen any results in the literature, at least under the name Quasirandomness, that would lead me to believe somebody has worked on this. I wouldn't be surprised if somebody working maybe under the language of equidistribution has talked about something along these lines. But in any case, I actually have a lot of thoughts on how that theorem might go, if you're interested in talking about it. It's something I've wanted to work on for a while. Okay, any other questions here?
Yeah, do all of these, do all of these pass back and forth between the spectral side, or like, if you tell me the subgraph count is this, can you actually produce the 4 cycles for me?
So yes, I can actually give you, so if I tell you something about the subgraph counts, you can actually, instead of all the little o1 terms, you can actually turn them into explicit epsilons and say that the count of 4 cycles would be upper bounded by some function of epsilon times, like 1 plus some function of epsilon times n to the 4th over 16. And in particular for this theorem, those bounding functions for epsilon, they're all actually polynomials. It's a fairly nice equivalence. Does that kind of get out what you were asking?
Yeah.
Okay. All right. Any other questions? Okay. So I'm going to be, I'll be talking about Boolean functions pretty much from here on out. And what do I mean by a Boolean function? What I mean is specifically a map from the vector space f2 to the n to plus minus 1. This is not the first notion of Boolean function that most people think. In fact, what's probably more likely is that people would think of replacing this with 0, 1 to the n, and then this with either 0, 1 or true and false. I actually have some very, very good reasons for not making this change. Here is sort of the motivation for it. We're going to be wanting to sort of, we'll actually want to use the vector space structure of f2 to the n. We're going to want to add inputs together quite frequently. Is going to come up when I start taking some notion of derivative on these spaces. The second part of it, this is the part that freaked me out when I first got into this subject, is -1 is going to be my notion of true. It's going to signal true, or normally what we would take to be 1 here. And 1 is going to now be false. Why is this? The way you should think of it is that I'm mapping to 0, 1, where they, honest to goodness, mean true. And then I'm going to feed it through the map e to the 2 pi I over 2, x over 2. So if I plug in 0, I'm going to get 1. If I plug in 1, I'm going to get -1. That's basically all that we're doing here. But it's going to put all of our outputs in the units in the unit group of complex numbers, which is going to be a lot nicer for what we're doing on, or what we'll be doing later. Also, it means that the function never outputs 0, which allows us to do some nice averaging arguments. Okay, so yes, Boolean function for the remainder of this talk will be some sort of map from f2 to the n to plus minus 1. -1 will be thought of as true, and 1 will be thought of as false. And I think it's probably best to give you guys a few examples, which are quite important. Both of these are going to be quite important in theory. The first one is the parity function. What this is going to do is return -1 if there's an odd number of ones in the input and 1 otherwise. And as a formula, it'll be chi of my input vector x is just -1 to the sum of all the input bits, where the addition in the exponent is taken mod 2. And my second example, this one will come back a little bit later, is the symmetric functions. Now, there are two different ways to define them. I'll stick to this one for the moment. They're going to be defined by the following formula that will be taking -1 to s choose k mod 2, and s is the total number of ones in the input. An equivalent way to define these guys is to sum over all subsets of size k of the product of the input bits in that subset, and then take -1 to this big sum mod 2.
So just to clarify, the parity function is a special case of the symmetric function when k equals 1?
Correct, yes. For a variety of reasons, these are thought of as extremely different objects. In particular, if you know a little bit of representation theory, you will recognize that this is one of the characters of the group f2 to the n, and all of the other characters can actually be represented as parity functions. The symmetric functions, as it turns out, are going to be sort of a very nasty class of functions for us to deal with. So we do want to think of them as separate for the moment. Okay, any other questions? All right. So now I'm going to have to build up a little bit of notation to start talking about what I mean by a random function. So this is the first time where it really matters that I'm thinking of everything as e to the pi I times something that lives in f2. I'm going to define directional derivatives of my Boolean function in a fairly odd way, in that delta sub v of f at x is going to be defined to be the product of f at x plus v times the complex conjugate of f at x. Way you should think of this is -1 to f x plus v minus f of x. And there's an equivalent way to do everything in terms of this sort of an operation, where I view f here as a function from f2 to the n to r mod z, or just to f2 if you're willing to deal with the abusive notation. Basically, this is all Nick, I'm doing here. Go ahead.
I thought f took values in 1 and -1?
Yes. And so let me maybe change my notation a little bit there to emphasize that. You're right, I'm mixing things up a little bit here. So let me do this as like g. This is going to be g, and then f is going to equal -1 to the g. Does that make a little bit more sense here?
No, sorry.
Okay.
Can you just explain what is the complex conjugation doing? Is that what you're trying to explain right now? Or
yes, yeah, the complex. So if f is equal to -1 to the g, where g is some function that outputs things in basically in 0 and 1, then when I do this complex conjugation here, I'm going to get so this will be -1 g x plus v times -1 to the g of x complex conjugate. And let me give you a little bit more of a reason why you might want to think of this.
Hold on. I think the confusion is that f is a function, and also -1 to the g is a function with values in -1 and 1. And when you complex conjugate those, nothing happens. So do you, by complex conjugation, do you mean swap the sign?
So there's a reason I'm being a little pedantic about this, is that if you consider some function which takes outputs in R, suddenly the complex conjugation does do something. And you're right, it does just change the sign of this guy up here in the exponent. We're going to need to consider functions like this very, very soon for some reasons that I'll be explaining. Basically, we can't stick to just Boolean functions here. And that is where this complex conjugation is actually going to come into play.
I don't know if we're going to get past this, but if you have a real valued function, complex conjugation does not do anything.
You're entirely right, but complex conjugation of -1 to a real valued function will change.
Oh, I see what you're saying. Okay. Interesting.
Yeah. Okay. Other questions? Do we still have some confusions on this here? Okay. I think an example will possibly help make things a little bit more clear. So I'm actually going to take the directional derivative of the parity function that I just defined previously. So what this is going to be is, as you guys noted, and I will keep the complex conjugation in here for basically for notational purposes. If I apply my definition directly, I just substitute in the vector x plus b into my first coordinate, and then the vector x into my second coordinate. Then I can reorganize using rules of exponents. And I've kept the negative sign here mostly just out of respect for notation. For this particular instance, it doesn't matter whether you keep it as plus or minus. But after I've reorganized, the x's cancel each other out. I get -1 to the sum of all of the components of v. And what this tells me, since v is a constant vector, is that the derivative of my parity function is a constant function for any choice of v that I want it to make. Okay. And you can also check from this definition, basically redo this same calculation, that the derivative at any directional derivative of a constant function is identically 1. And so we can make the following definition. If I give you some function that maps into the unit complex numbers, and for any choice of vectors, I pick d different vectors. If I take these iterated derivatives and I get the constant 1 for every input, then f is going to be said to have degree at most d minus 1, or degree strictly less than d. And this is going to be, in some sense, my measure of how not random a function is. Or another way to put it is, low degree functions are not going to be thought of as random. And you can check through some computations, but it's fairly easy to prove that in expectation, a random function is going to satisfy this equation about half the time. So a low degree function, which will satisfy this all the time, should be thought of as quite far from it.
To clarify, Nicholas, is this like the same notion of degree if like expanding out on like the Fourier basis, that like each of the terms is like?
It is not.
Oh.
This is actually and that is one of the more interesting parts of this theory. So what Sam is asking here, there is a beautiful basis for all. The representation theoretic basis for Boolean functions is defined in terms of parity functions. You can define a notion of degree by how big of a parity function do you need to express my function. That is actually not the same notion of degree that we're going to be working with here. This one is, in fact, a stricter, a much stronger notion of degree. There are functions that are degree 2 with respect to this notion, that are degree n with respect to Fourier degree. Okay, yeah, very good question. Any others before I move on? Okay, so as I was mentioning on the previous slide, one way that we could sort of test what degree our function is to look over all possible vectors and see how often do we have the derivative equal to 1. And this will give some notion of how far things are from being degree e. And more formally, I'll define something called the Gowers norm of f, defined by this horrible looking formula. And what this really, the way you should read this is I'm going to sum average over all possible choices of my directional derivatives and all possible points average, the value of the directional derivative, and then this is just a normalizing factor to make the norm equations work out. And I will make a fairly naked play for a question. Are there any analysts in the audience who are going to call me out on the egregious misuse of notation that I have made here?
No, it's acceptable. I'll take it.
Okay. The particular question that I am asking for is how the heck do I actually get to call this thing a norm? It is, in fact, a norm. It is a fairly unpleasant proof that involves applying Cauchy-Schwarz to itself d times. I can show you the notation if you want. Please don't make me do it. It's unpleasant. The point being, and the way that I want you guys to read this, the Gowers norm, what it is doing is looking over all possible ways of taking directional derivatives, over all possible points, and just averaging up how often do we get one, how often do we get -1 or something else. In other words, this thing is measuring sort of how close are we to being a degree d function. In particular, if I give you a function of degree strictly less than d, all of these derivatives are going to be 1. The entire expectation cancels out. I get 1. And to give you a little bit more of an idea of what these things look like, let me actually do a quick expansion for d is equal to 2. So I'll start off, and I will almost immediately take this -2 to the d out, put it over on the other side. It's going to make my life much better. And, well, expand out by definition. I'll start by applying my definition of directional derivative. I'll get this guy. And now for the next step, it's a little bit annoying. I have to take 2 copies of both the f of x plus v and the f of x, keep the complex conjugations in the appropriate places, and we'll end up getting this big old nasty formula down at the bottom. Notice that if I complex conjugate f of x twice, I'll get back to the beginning. The other conjugations end up with this. Okay. So I want to look a little bit closer at this expression here. So when we expanded everything out, we got this big old product. Please ignore the fact that I wrote sum here. I'm going to read this in a slightly different way. That I'm taking a product over every element of an affine subspace, specifically the space vector x plus the F2 span of v and u. Now, if you remember when I talked about the general idea of what a quasi-random theorem looks like, we already talked about how there was some sort of count of small sub-objects. This is going to lead to that property. In particular, if I fix a n by d matrix in F2 to the n, think of this v and u as representing an n by 2 matrix and a base point x, I'll say that a fixed function g from F2 to the d to plus minus 1 embeds in my big function f2 to the n to plus minus 1 if f at x plus mb is exactly equal to g evaluated at v for every v. Another way to put it is if I restrict f down to this very, very small affine subspace, I get exactly the same function as g. And this is where it's important that I actually keep a specified basis and choice of base point for the function when I'm doing this restriction. Okay. And since this thing is going to be for counting small subobjects, I'll define M or embed of G and F as the count of the number of matrices and base points where G embeds in F at that particular matrix, divided by the total number of matrices and choices for X. Okay. And so one last little thing. I've already used this notation, but I do want to mention it explicitly. Instead of stating things in terms of sums in this main theorem, I'll just be stating them in terms of averages, even though there's actually no randomness going on. And in particular, when I write expectation of something, it just means the sum of whatever that thing is divided by 2 to the n. Similarly, if I'm going to be talking about some subset of f2 to the n, the probability that x is in x is an element of S is just going to be the size of S divided by 2 to the n. And I get some practice with that notation. I can define an inner product on this space as you would with the representation theoretic inner product via the expectation over F2 to the n. And last but not least, I'm going to take things a slightly different direction. So I give you a bunch of functions of degree at most d, where degree is in the sense that I was describing earlier. I'm going to define a variety based off of these guys just to be their common zero locus, all the points where every single one of these polynomials gives me the value of 0. Okay, with all of this stuff in hand, I can finally state my main theorem. And afterwards, I get to tell you a short story. So I fix some function f2 to the n to the unit complex numbers. And in particular, it's a Boolean function, so it maps to plus minus 1. And I'm going to fix an integer d and epsilon greater than 0. D is going to be thought of as our degree bound, as in functions of degree d or smaller are going to be considered definitely not random. Anything that is random is going to have higher degree. So the following are equivalent up to losses that depend only on epsilon and d. The first property, which I'll call the Gowers norm property, is that the dth Gowers norm of the function is at most epsilon. Remember that epsilon, that if Gowers norm is small, it means our function is far from degree d polynomials. Second property is the correlation property. The inner product, as I defined on the previous slide, in absolute value of f with any function of degree strictly less than d is going to be at most epsilon. My next property will be the discrepancy property. This says that the average of f over any variety of degree d, notice this doesn't depend on a codimension or how many polynomials are used in the variety. This is going to be upper bounded by epsilon divided by the probability that I land in that variety, roughly the measure of the size of the variety. Finally, we'll have the embeddings property, that the number of embeddings of any fixed function on d bits is about what it would be in a uniformly random function. And last, we have a structured embedding property, which says that the constant functions for every size from 1 all the way up through d, they all embed about as often as they would in a random function. And the claim is that all 5 of these properties are going to be equivalent to each other up to some changes in the parameter epsilon, which only depend on d, and epsilon does not depend on n, which we can again think of as large. So since I've been stating so much about the notation here, are there any questions on what this theorem is saying?
Yeah, so one small thing. So on the discrepancy thing, if I understand it correctly, this is intuitively strongest when b is as large as possible?
Yes.
Is that correct? Okay.
Yes. So if you think of the example you should think of here, set v to be the 0 set of a single function. In particular, think of a parity function. So all inputs which have an even number of zeros, or an even number of ones, excuse me. If you think of that as my variety, that's a fairly large set. It's volume 1, it's half of the whole space. So this probability that x is in v is now 1/2. Epsilon you should think of as approximately 2 to the minus n over 2. So this is tiny. And this is saying that the average of my function over that space is very, very, very small. If I were to put in more polynomials here, this probability starts to shrink very, very quickly, and this bound decays with it. Okay. JJ? Okay. Are there any other questions here? All right. So before we proceed,
sorry, I was muted. My bad.
Okay. Yeah.
How do the statements in this theorem hook up to the 4 four part, like the ones that you showed with the graph, like the
Great
structured
question.
sub-objects and small sub-objects?
So this is going to be my sub-object property. This is going to be my structured. This is going to be my average over sub-objects. And then these two together are actually going to be my Fourier property. And this has some major scare quotes around it. Does that kind of answer your question a little better?
Yeah.
Okay, good. So I will not be going through and proving this theorem in full. You'll see why in just a second, because here is the outline of the proof. Every single one of these arrows is an individual lemma. This is the reason why I don't want to go through the proof in full. And what I've written here, the little function on each arrow represents the actual loss when proving this lemma. So in other words, I would need to, in order for the Gowers norm property to imply the embeddings property, I need to assume with bound, in order for Gowers norm with epsilon prime to apply, so if this is epsilon prime, then if I set epsilon prime to be this in the Gowers norm property, then I get a bound of epsilon in the embeddings property.
So
likewise, go ahead.
Just to be clear, I don't think I got this from before. Is D fixed and
Yes.
epsilon is, oh, okay.
Yeah,
So these are
D
the
is
functions,
fixed.
these are the functions that describe how you transfer from one epsilon to the other epsilon.
Exactly, thank you, yeah.
Okay.
Yeah. So yeah, as Vaki was just saying, that when I mentioned, and actually grateful that Thomas asked about this earlier, that these are exactly the bounds that you get when going from one property to another. And to give you some idea of the proof, these guys, these all very much mirror the proof that a Gowers norm is actually a norm. This over here is a fairly well-known lemma regarding the Gowers norm. This over here is some exponential sums, and this is the remainder of my talk. So
Who is TZ?
that is what I'll be talking about in a second. So the keywords to look over here. So over here, we use a bunch of results on exponential sums. Over here, we use something called the Cauchy-Schwarz-Gowers lemma. And then up here, this is another well-known lemma. So roughly speaking, the proof is just a lot of individual lemmas that when all put together end up with one big old result. Except for this guy. As Sam was just asking, TZ is a paper by Terry Tao and Tamar Siegler from 2011. And it's going to be about the problem I want to talk about now. So, okay. Previously, what we said is if I give you a function of degree at most d, the Gowers norm, the dth Gowers norm must be 1. So, what about the converse? If I give you a function with dth Gowers norm 1, what can I say about the structure of f? And this is where I'm going to have to start taking those complex conjugations into account. There's a very good reason why I've kept them for the entire time. So I'm going to define a function. It's not a Boolean function, but it satisfies the same notion of degree. I'll define the function iota from f2 to r by iota of 0 is 0 and iota of 1 is 1. I'm going to consider the function -1 to the iota of x divided by 4. So this is a function from f2 to the unit complex numbers. Specifically, it maps into the 4th roots of unity. And I'm going to take its derivative in the direction 1. So what that means is I'll just compute by my definition of derivative. This is going to be iota of x plus 1 divided by 4 minus iota of x over 4. And because I'm essentially working modulo 4 in the exponent, that -1 is now 3/4. And now things are going to get a little weird. Let's say I plug in 0. So if I set x equals to 0, then iota of x plus 1, is equal to 1. Iota of x is equal to 0. So my overall result that I get should be 1/4 up in the exponent. If x is equal to 1, then iota of x plus 1 is equal to 0. Iota of x is equal to 1. So I get 3/4 in the exponent. Putting these two facts together, this is the function that I get. -1 raised to the 1/4 plus iota of x over 2. And to write it in the notation that I've been using previously, this would be -1 to the 1/4 times the parity function on 1 bit. So we established earlier in my first example that the parity function has degree 1. What that means is this function has degree 2. But you'll notice its outputs, they live in the fourth roots of unity, not the second roots of unity, like I've been working for the entire previous part of the talk. And what's going on here is I have a degree 2 function. It's a totally valid degree 2 function. I'm going to call this thing, following Tau and Ziegler, a non-classical polynomial. In other words, something where they lie in the 2 to the i-th roots of unity, possibly up to a rotational shift. And finally, we do get a nice equivalence that, as shown in that particular paper, the dth uniformity norm is 1 if and only if I give you a possibly non-classical. Great. So in that red implication in my theorem, one way to restate it is that if I have small correlation with all maps of degree at most d, then my Gowers uniformity norm must be small. And I've stated that here, that if I have correlation at most epsilon, then I have some function phi of epsilon d that is an upper bound of my uniformity norm. So it'd be really great if I could just ignore everything that I talked about on the previous slide and only compare correlations with functions whose outputs are plus minus 1 and still get this, this implication right here. In other words, only consider classical functions whose outputs are in the second root of unity and get this implication. And then we have a theorem by Lovett, Mishulem, and Sabornitsky from 2007. You might recall my second example of a Boolean function was the symmetric functions. They're going to be our bad guys here. The fourth symmetric function, it has a very large, as these things go, uniformity norm. Notice that this bound is independent of n. So no matter how big I make n, I'm going to have a fairly big uniformity. But it has extremely small correlation with every classical function of degree as controlled by this uniformity. The upshot here, I need to consider non-classical polynomials in order to prove this main theorem. And to put it quite bluntly, there are a lot of unanswered questions about what non-classical polynomials look like. For instance, we have no idea how to characterize what their level sets look like. We have very little information about, we do have a normal form for all of them, but it's still fairly unclear, even finding a good basis for all of these things. There's still some debate over how to actually write them all down in a nice way. And that doesn't mean you can't get around them. In the paper that I cited from Tao and Ziegler, they did actually prove that implication in my main theorem. If I have low correlation with all non-classical polynomials, then my Gowers norm must be small. They proved the converse of that if the Gowers norm is large, then I can find some delta and some non-classical polynomial p for which the correlation between f and p is at least delta. You might wonder, how big is delta as a function of d and epsilon? We don't know. There's no effective lower bound. This is one of the issues of doing proofs using non-standard analysis. And Tao himself has said that if you go back through the proof and try to finitize it and actually get a lower bound on delta, it's probably not worth your time. The value that you'd get would be so small. That doesn't mean people have not continued working on it. As of last year, Gowers and Milicevic proved a beautiful, beautiful intermediate result in additive combinatorics that would actually give a somewhat decent lower bound on delta, if this is your definition of decent. But it doesn't work for the setting that I happen to be presenting here. This result, in order for it to imply this inverse theorem for the Gowers norm, it requires the characteristic of my field to be larger than the degree of my polynomial, which there are analogs for all of the things that I've talked about over fields of F over F3, F5, F mod P. However, these characteristic issues really start showing up quickly. And I'll finally close that Jonathan Tidor over at MIT recently put out a nice little result where he did actually manage to circumvent the characteristic issues for, I believe, everything characteristic greater than 2. So even it doesn't apply to what I've been talking about, but it only works for d is equal to 4. So in other words, this theorem that I've written up here, you can substitute this lower bound in, but only if d is equal to 4 or smaller. And beyond that, nobody knows what the lower bound is. We have lots of conjectures, but it is a major area of major open problem in additive combinatorics at the moment. And so with that, thank you guys for listening.
All right, let us thank the speaker. Does anyone have any questions? I have one.
Yeah, go ahead.
Can you go back to any one of the quasi-randomness theorems from the beginning, from the middle, wherever you want?
Let's just go back to the main one. That should be.
That sounds good.
Yeah.
Can you? I always get confused with these theorems. Can you say exactly what it means to be equivalent up to losses, which only depend on epsilon and d, just for the first two, say?
This is the slide you're going to want to look at for that. In particular, so let me maybe write this down a little bit more formally. If so what I want to say here is that and you were referring to these two guys.
Sure.
If I want to say that the absolute value of the inner product between f and any function of degree at most d is at most epsilon, I need to assume that my Gowers norm, in this case, is also at most epsilon for this to be true. Over here, to prove that the number of embeddings of G and F is at most epsilon, then, if you will, the delta in my epsilon delta proof needs to be smaller than this. That's probably the best way to state it.
But, meaning your Gowers norm has to be smaller than epsilon over 2 to the d plus 2.
Yes.
Yeah, okay, so all it is this statement seems easy. If the Gowers norm is less than epsilon over 2 to the d plus 2, then the distance you're embedding this difference that you've written is less than epsilon.
Yes.
Okay, and that's basically how all of them work.
Yep. Yeah.
Okay.
And in particular for that statement, it would be that for every function g.
Yes.
Yes.
Okay, sweet. Thank you.
Yeah.
Any other questions? All right, let us thank the speaker once more.